Limiting reactant problem number 2. Things to remember. The limiting reactant is the reactant that limits the amount of product that can be made. That means it is the reactant that can make the smaller amount of product. Therefore, it is the reactant that can make the smaller amount of product. The excess reactant is the reactant that will have some left over at the end. There will be a little amount that's in excess. The reactant that has some leftover at the end. It's the reactant that would make the larger amount of product if you had enough of the other reactant to make it. Okay, therefore, it is the reactant that would make the larger amount of product. So if you're looking in a question and you want to determine who is the limiting reactant and who is the excess reactant, you therefore need to determine the amount of product. And if you determine the amount of product that can be made from each reactant, you're going to be looking for the one which is smaller, because that means that if you're looking for the one that is smaller, you will have found your limiting reactant, and you can use the limiting reactant to do any further calculations. So let's again do an example. In this case, we are looking at a synthesis reaction. We're going to take sodium and chlorine. Remember, chlorine is one of our diatomics, so it has to be Cl2. And that's going to form sodium chloride. In any limiting reactant problem, it's a stoichiometry problem. If it's a stoichiometry problem, your reaction must be, that's right, your reaction has to be balanced. So let's balance this. We need 2 Cl's on the right, which means that we'll need 2 NAs on the left. And our question here is what mass of sodium chloride can be formed when 1.7 grams of sodium and 2.6 liters of chlorine gas at STP are reacted. So first, how do we know that this is a limiting reactant problem? Because this question doesn't say the word limiting anywhere. It doesn't say the word excess anywhere. You know it is a limiting reactant problem if you are given quantities of two different reactants. So here's reactant A, and here is reactant B. And if we have two different reactant quantities given, then it is a limiting reactant problem. Okay, so we know we have a limiting reactant problem because we have one quantity of a reactant given and we have a second quantity of a reactant given. And in order to find the actual amount of product formed, because this is our product here, in order to find the amount of product formed, you're going to have to find the amount of product that can be formed from reactant A and the amount of product that can be formed from reactant B. So, find the amount of product, and in this case, it's usually easiest just to go to moles. Then if you need to convert it into liters or grams later, you can do that. So find the amount of product in moles that could be made from each reactant. So reactant A, that is our 1.7 grams of Na. And in this case, our product, we only have one product, NaCl, so we're going to use that as our product. Always take your reactant and convert it into moles of reactant. Step 1, convert into moles of reactant. So we want to cancel grams of sodium and find moles of sodium. And the molar mass of sodium is 23.0 grams per mole. Once we have moles of our reactant, we can find moles of our product, which in this case is NaCl. And we will cancel moles of sodium. And the coefficients for those two, we have a 2 in front of the Na, so there are 2 moles of sodium used will produce, and there's a 2 in front of the NaCl, so there will be 2 moles of NaCl produced for every 2 moles of Na used, and that gives us 0.0739 moles of NaCl. So that's how much we could make from our sodium. Reactant B. Find the moles of product that could be made from reactant B. In this case, 2.6 liters of Cl2 gas. And this is a gas at STP, so we need to cancel our liters. And of course, the first thing we're doing is finding moles. Remember, the first thing you do in any stoichiometry problem is you find the moles, okay? So we're finding moles of Cl2, and there are 22.4 liters per mole, per 1 mole. Okay. And now we will use the mole ratio to convert moles of Cl2 into moles of product, in this case moles of NaCl. How do we know the mole ratio? We use the coefficients from the balanced equation. So backing up here, we see that there's no coefficient, so that's a 1 Cl2 for every 2 NaCl. So there's 1 mole of Cl2 for every 2 moles of NaCl. Finish our calculation and we get 0.232 moles of NaCl. Take a moment, pause the video, and say to yourself, who of these reactants is the limiting reactant? Is it, okay, so here's the question for you. Who is the limiting reactant? Is it Na? Is it Cl2? Or is it NaCl? Pause your video, answer that, and when you're ready, come back and find out. Okay, so in order to find out who is the limiting reactant, you have to look and say who produces the smaller number of moles. Is it A or is it B? And in this case, you get the smaller amount of moles here. But that doesn't mean our limiting reactant is NaCl. NaCl is the product, so it cannot be the limiting reactant. We have to go back and say who was the reactant that made that much, and that was our sodium. So our reactant, our limiting reactant, is the sodium. Okay, and finally, this question asked us for what mass of NaCl can be formed. So we're going to use this amount of sodium chloride, that many moles, to find the mass of NaCl that can be produced. So mass of NaCl produced is 0.0739 moles NaCl times the molar mass of sodium chloride is, hang on a second, that looks wrong, 35.5 plus 23 is 58.5 grams of sodium chloride per 1 mole of sodium chloride. And that gives us 0.0739 equals 4.3. And I look back and I've got two significant figures here, two significant figures here. Not that that one matters because we're not using it. So we're going to have two significant figures here. So this is 4.3 grams of NaCl can be produced. Don't forget, it's always nice to box your final answer. Okay, and that's it for that question. Stay tuned. Next time we'll be going into finding how much excess reactant is left over after the reaction is completed.